set of facts that were used to explain a phenomenon in 1911, and that same set of facts was actually used on this 1918 example, even though the two examples did not equate. Okay. So, is symmetrical time dilation possible? Meaning reciprocal, meaning equal and the same. During the inertial portion of the traveler's journey, his clock will be seen as ticking slower by his twin brother on Earth, while at the same time the traveler will also see his brother's Earth clock ticking slower too. So this would be symmetrical or reciprocal. And again, it's the opposite of everything we know about common sense. Anything that's different about me and you would be seen as equal but opposite, but in this case it's equal but the same. Your clock slows down from my perspective, and at the same time you're looking at my clock, and my clock also slows down from your perspective. It doesn't make much sense, but it doesn't mean that it's impossible. It's difficult to conceptualize, but still possible. There's a lot of other areas of physics that are very mind-blowing and surprising to scientists when they come upon these discoveries. Many aspects of quantum physics is one. There's a lot of things to quantum physics that defy common sense and are very difficult to conceptualize, but yet there's a lot of experimental evidence that has shown that is the case. So we can't throw something out just because it just seems funny to us. Is there a test that will demonstrate this symmetrical effect in Einstein's theory needed to preserve Galileo's principle? Right? Because again, Einstein, not everybody went this route. As you can see, there's a big variation among expert scientists out there in using the various steps of a journey of a spaceship leaving Earth, going all the way out at constant velocity, turning around, having gravity or acceleration, and then coming all the way back, and there being a difference between what the clocks say when they reunite. Again, we've seen a whole host of different explanations. There isn't anything even close to a consensus on what happens. But Einstein says, being very mindful of the implications of Galileo's principle and wanting to preserve it, that when any two are in a state of relative motion and neither are accelerating, one will see what the other one sees too. They will both see each other's clock slow down at the same time. So is there a test that will demonstrate this very bizarre symmetrical effect in Einstein's theory needed to preserve Galileo's principle? Here it is. A lot of people have GPS receivers in their car now. Some need them more than others. I can still drive around town without getting lost for the most part, but the last time I was out of town and I didn't have a GPS, it was kind of a nightmare. So that was it for me. I bought one, and now every time I go out of town, I've got a much less stressful trip. The Global Positioning Satellite System is something that actually uses atomic clocks, very, very sensitive, very, very accurate atomic clocks, and they will basically keep time down to the nanosecond, which is a billionth of a second. So that's pretty accurate. And something like that is important because we're not talking about very, very high velocities, nor are we talking about very, very long time periods. So any Einsteinian or relativistic effects that would be observed with two different clocks that are going two different velocities or that are in two different places in a gravitational field, these atomic clocks can be taken advantage of in this GPS system to see if we can use this to see if all of what's said about relativity is consistent or not. So first, a little primer on how the GPS system works. How the GPS knows where you are. Let me use cell phone towers as an example first, okay? So let's say that I've got my cell phone, and there's a cell phone tower right here, and somehow the cell phone tower knows how far away me and my telephone are away from that tower. Doesn't know what direction I'm in, it only knows the actual distance. So if I'm 50 yards from the cell phone tower, then I could be 50 yards in any direction, and the only information that I know is that I'm 50 yards from cell phone tower A, right? So since it could be in any possible direction, I could be anywhere on this circle here. That could be my position. But let's say that there's a second cell phone tower somewhere else, and my cell phone also knows that I'm 45 yards from that particular tower. Again, it could be any possible direction, but if both facts are true, if I'm 50 yards from this tower and 45 yards away from this tower, then there's only two possible positions that I could be in, right? Because to be 45 yards anywhere over here, and I'll be way farther away from the 50-yard mark on this tower. So once I know both of these facts, I can take advantage of that and narrow my position down to 2 possible spots. If I introduce a third cell phone tower, then that third cell phone tower, and let's say that I'm 20 yards away from that third cell phone tower, then again I could be 20 yards in any direction, but knowing that I'm either here or here already, then that finally narrows my position to only one possible location. And that possible location is right here, because this is the only one place where I can be exactly 50 from here, 45 from here, and 20 from here, okay? GPS works the same way. Instead of cell phone towers, we're actually talking about satellites floating around up in the sky that have very, very sensitive atomic clocks and can actually track the distance between you and that particular satellite. So, and actually they use more than 3 satellites, typically, usually 4, but just to stay consistent with our explanation here, let's say that if it were 3, if I was on some position driving around here on some road here and wherever, then my GPS receiver will receive communication from satellite number 1, satellite number 2, satellite number 3, calculate the position from each one of them, and come up with one possible location where I can be. And so my satellite receiver on my screen that basically says, I'm on such and such a street, and you can see how accurate these things are these days. You can not only see what street you're on, but you can see what 2 blocks that you're in between and where your next right turn is going to be. So these things are pretty accurate because the atomic clocks on here are really the driving force between how they can accurately determine what your specific distance is from each one of these satellites. Okay? So the GPS satellites and ground control stations use precise atomic clocks to determine locations with incredible accuracy. Clocks measure time in nanoseconds, which are each 1/billionth of a second, and the system needs to be synchronized in both directions in order to work properly. We have all kinds of communication going back and forth between the two. The satellite is receiving periodic corrections from the ground control stations, and the receivers are getting ongoing time signatures from the satellite. So it's very, very important for this system to be synced 2 ways simultaneously in order for everybody to be on the same page time-wise. Okay? Satellite clocks floating way up there, about 11,000 miles off the surface of the Earth, so they're up there. They're in a higher gravitational position and will run at a faster rate than ground clocks unless adjusted, right? Because that's what we've been saying from the beginning, is that gravity will slow clocks. So if you take a clock out of gravity, it will suddenly start to run faster. And this is a little less confusing than the constant velocity portion, or the special relativity portion, because at least we can conceptualize this a little easier. If Einstein is correct about all of this, then at least we have an equal but opposite effect. If I've got a satellite clock up there and a ground clock down here, then I will see the satellite clock running faster, but the satellite clock will actually see my clock on the ground running slower. So it'll be an equal but opposite effect, something a little more palatable for us to understand. Satellite clocks are in a higher gravitational position and will run at a faster rate than ground clocks unless adjusted. Okay, you can actually, and these are frequency generators that is actually acting as the clock, but anything can be a clock. Light pulses can be a clock, a wind-up spring could be a clock, and basically anything that has some sort of mechanism to it that's at timed intervals could be thought of as being a clock or used for the purposes of keeping time. So in this particular case, the frequency generators on the satellite are kind of run by these atomic clocks here. So knowing that the clock is actually going to run faster when we transport it up to 11,000 miles off the ground, we can actually slow it down and compensate for that before we launch that clock up on the satellite. And that way, with that clock running slower here on Earth than a typical clock, once it gets higher up out of our gravitational field, it on its own will speed up. But because we slowed it down ahead of time, it'll be running just right, meaning that it will actually be in sync and be running at the same rate with our clock here on Earth. Satellite clocks, as we said, are also in constant motion, which contributes to running slower than stationary clocks on ground. So we have two different effects going on here. And we've been talking throughout that we've got special relativity effects, general relativity effects, and in the case of GPS, we actually have to consider both at the same time. So the higher position of the satellite compared to ground level actually causes the clocks to run 45,000 nanoseconds per day too fast. Now, to you and me, that might not be a big change, but to atomic clocks that try to gauge the position of a GPS receiver right down to the meter, 45,000 is huge discrepancy if that's not accounted for. The constant velocity portion would be 7,000 nanoseconds too slow. Again, the higher clock is moving away from gravity, so that's causing that to run faster. But at that same time, it's also in motion, and the relative motion of that clock compared to us on Earth as we're watching it fly overhead is causing it to run 7,000 nanoseconds per day too slow. So if one is producing a 45 effect too fast and the other one is 7 effect too slow, we wind up getting a net error of 38,000 nanoseconds per day too fast, because we just add the two together. Having said that, both effects, and other minor effects too, but these are the two primary ones, all the effects are compensated for in advance. So prior to launch, the satellite clocks are adjusted to run 38,000 nanoseconds per day slower, so that when they are placed in the high altitude orbit, they are actually running in sync with the ground clocks. Again, if we don't do that, if we just leave them be and then launch them, we're in trouble, because then they're running way too fast once they're up there. But if we know that ahead of time and we actually slow them down before we launch them, then they're running slow on Earth, but then we transport them up to a higher position away from the gravitational field, and they speed up to just the right speed, and now they're actually running at the same rate. So if a satellite became magically suspended, 11,000 miles is about 20,000 kilometers metric conversion, with no velocity, we would only have to gravity adjust the clock. So if we can just imagine for a moment that this satellite here is not in orbit, but it's just magically suspended, not moving back and forth, just hovering over a particular position, then the only thing we would have to worry about at that point, because it would have no velocity, is the 45,000 nanosecond per day adjustment, because it would be the gravity adjustment only, right? Now, if we did that gravity adjustment before we launched it, we would do the full 45,000 nanosecond per day slowdown. We would slow it down by 45,000 nanoseconds per day. We'd launch it. We'd magically suspend it in a fixed position 20,000 kilometers above the Earth. It wouldn't be in motion, so we wouldn't have to worry about that other 7,000. So we're just compensating for the 45,000, and we magically suspend it. If we do that, and we offset the clock by slowing it down by 45 ahead of time before we send it up, once it gets there, it will be running in sync. It'll be running in perfect order, and we will be able to do a two-way syncing system between the satellite and the ground. Okay? So the satellite clock is slowed down by 45,000 nanoseconds per day prior to launch, and then once we launch it, then what happens is it's running at just the right speed, and everybody's happy because everyone is sync, right? The ground clocks and the satellite clocks would operate in sync, okay? But then we take that satellite and then we start to put it in motion. And what happens when we put it in motion? Now something happens and it falls out of sync. So now we put it in orbit and it starts moving, and it's moving at just the right velocity to maintain orbit at that height, which basically gives it enough velocity to cause a 7,000 nanosecond discrepancy, right? And what we're going to do is we're going to take a look at what those effects are and how we can use that for special relativity, and analyze the possibility of whether both clocks see the other one slow down simultaneously, and whether it's even possible for the GPS system to be synced two ways at the same time and have that fact be true about special relativity.